So I built a governance contract and then deployed that to base Epolia while keeping every single details confidential and encrypted on chain, while still preserving the transparency nature of the blockchain. And I didn't use zero knowledge proof here. Instead, I used a tool called Inco. Inco is a full stack privacy suite that enables you to develop confidential smart contract right within Solidity. They do this by giving you custom data types which are encrypted, which would allow you to encrypt the data of the user, and custom operators and then programmable access control, allowing you to architect your smart contracts in a way that it preserves the privacy of the user. And then not only that, and every single sensitive operation that you do on a smart contract happens inside a TEE environment. TEE stands for Trusted Execution Environment, which is a small space inside a processor where data goes in encrypted, gets decrypted, gets executed, and then comes back as re-encrypted, and none of the outside elements of the processor can access it. It's a very small black box where execution happens. And this is how Inco executes everything. And it's not ZK, it's not FHE as well. It's a complete different concept where they give you data types and other stuff like this to build your smart contracts with the same solidity we'll be building throughout the decade. To make things simpler, they also have their own skill as well. It's called Inco Lightning Skill, which is very good to use because you can just one shot any sort of applications you want with their skill. You can click here, build with AI from the documentation, and you'll be able to install their skill, and this will allow you to build confidential smart contracts using in-course data types and operators uh, in no time. Alright, so I have my cursor open here, and I just use that skill lightning, that's the skill name. And then all I said was that can we set up a simple project which implements a governance contract, allows user to become a member by holding a token and cast their votes, create proposal, etc. And I also added this one prompt that allows me to allows the AI to make better decisions on how to build this application. So everything went through, and then we have the entire contract ready. So just let's have a quick walkthrough of the contract. So first thing we need is a token, right? So every member should hold a token. So as you can see, it's actually similar to how we built an ERC20 contract with Solidity. The first thing we're doing here is we are importing those required components here, like EUint, eBool, E and Inco from Inco's library. And EUint is actually the Uint data type, but it is encrypted here from Inco. So as we can see, we are using that to map the balances, which allow us to keep the balances encrypted. And then again, we are using EUint to also encrypt allowance as well, so even we can keep that as encrypted. And then the address remains the same as the Solidity we already have. And then we have some errors. We have some additional function like qualified for, and other few more function like an encrypted mint function, which will allow us to mint tokens for our members in an encrypted way or a confidential way. And then this requires a fee for ciphertext input. So since we are sending a bytes encrypted amount, basically we're sending the amount as encrypted, and this requires some fee for the processing of this confidential function. And Inco expects us to send this fee via message.value. So if you're dealing with encrypted functions or encrypted block of code, you will be expected to send some fee. Next up we have transfer. So transfer here is similar to how we have in other ERC20 tokens also, but there's a simple twist here. One of the functions we have is something called new EUint 256. So this is a factory class or factory method that you can say, which will allow you to use additional functionality of a EUint. So basically you can, if you want to call add, subtract or multiply or some other functionality that you want to do on an integer. So what happens is that with bytes you cannot do that, right? And your value input here is encrypted basically, and you're sending that as a bytes, but input is a number, let's say 1 or 2 or 3, and then you want to do some math or something like that. This EUint256 will allow you to access those methods, built-in methods from Inco. And then we are using message.sender here because, as I said earlier, it requires a fee, and this entire fee calculations and its submission will be handled internally, and that's the reason we're using message.sender over here. And the reason why we're using this is that the encryption that we do off chain to send this value, basically we would use a JS SDK, which I'll show you later on, to do the encryption, and it should the encryption should be done by the same address that is the caller here, or else it will be rejected. Okay, this is just an anti-spoofing cautionary check here. Similarly, we have some other function like approve, transfer and other stuff as well, and these are some internal functions that we are dealing with here. Okay, so all in all, a simple ERC20 contract that we already have with some of the Inco's confidential data types over here, and next we'll move on to the actual governance contract. Alright, so we're in the governance contract now finally, and then we have ported the same stuff again that we saw in the membership token contract as well. And then we also have one more thing called decrypt attestation. So this is used to decrypt your TEE environment execution attestation. So when you execute something with TEE, you get an attestation in return as well, along with your output or whatever you're expecting, and you can basically verify that attestation to validate that whatever the software or whatever the code that you're running was actual code that actually ran inside the environment, and then whatever the output you see is actually valid. That's why you would verify the attestation, and that we are decrypting the attestation and then verifying it. So moving on to the actual logic, we have struct of the proposal. So we have description, deadline, yes, no, revealed, yes, no, results, so on and so forth. And then we have membership token reference over here, and then we have a threshold, encrypted members, joined, and encrypted members, as you can see, we are using ebool, so encrypted boolean, and similarly we have some errors, events, constructor. Okay, join DAO. We're registering the members by checking their token holding. So if they are qualified for, meaning if they have the amount of threshold tokens in their account, so we're gonna say yes, we're gonna qualify them, or else we're gonna reject them. And then we are creating a new proposal here. This accepts like description, voting period, etc., etc., and then returns a proposal ID. And we can see we're just pushing it like a normal usual smart contract logic, nothing else. Now we have cast vote, so where people can vote yes or no, and which is encrypted of course. And then we have encrypted e-boolean, true equals yes and false equals no. So remember, we're not accepting true or false directly in the function and then encrypting it inside the smart contract. So when it comes to the smart contract, it's already encrypted off chain, okay, using the SDK of Inco. And we're basically checking for some insufficient fee, or insufficient fee is required because since we're dealing with encrypted data, we need to be able to pay for that processing as well, right? Because we discussed that in the previous contract, so that's the reason we're using this. Similarly, we are just doing some sort of calculations over here, updating, adding. As we can see, we are using add. We're using new ebool, similar to new EUINT before as well, which will allow us to call these sort of functions so that we can perform operations on them, like compare them, check them, add, remove. Alright, moving on, we have finalize. This is where we'll be submitting our attestation. So here we can see we are accepting the decryption attestation as well over here that we imported from the types that we have. So we'll be getting the decrypted attestation off chain using SDK, and then we're gonna send that over here, okay, to finalize the function. And then we are actually checking it. We are doing it inco.inco verifier is valid decryption attestation. So if it is valid, if it is not valid, then we're going to revert. If it is valid, we're going to keep it. Okay, so because we need to make sure that this exact computation ran inside the enclave, right? And then we were able to verify it, so that we're not running something else and then proving that it works. Okay, so you can see the entire pattern here, right? So everything is encrypted on one end, everything is still on blockchain, so it's public while still being encrypted. And then even the execution that happens is trustless, so you don't have to trust that, okay, I'm executing this on AWS or executing this on someone else's server. How can I trust that server is not running some sort of backdoor or some sort of spying software or something like that? Since it's running inside TEE, you can confidently say that it is trustless, because TEE doesn't run multiple stuff at once. It only runs one thing that you provide, and whatever it is running, the code, the binary, your code, whatever it is, everything is mentioned in the attestation, so you can validate end to end. You can make sure that even the version of your software is correct or not. So that's the entire beauty of it. So everything here is trustless, everything here is encrypted and confidential. So moving on, you have proposal count, get proposal, so on and so forth. Okay, like a very simple governance contract. So now let's move on to the JS SDK part. I'll show you like how I'm calling these functions. I don't have a UI, I just have a simple script file that I've written. So I'll show you like how I call these functions and everything. Alright, to keep everything simple, I'm gonna just show you the encryption part because that's the main important thing here, right? Apart from that, everything is just straightforward. The first thing is we're doing, obviously we are using Inco Lightning JS SDK over here. This is officially a link Inco library, and coming back to finalize over here. So first thing we're doing is we're reading the contract to get the proposal. So we're getting the proposal of the ID that I've provided. Okay, and then we're doing some sort of precautionary check. If it is already finalized, we have to just say like, hey, it's already finalized, right? And then we reveal the tally. Basically we reveal the tally that we saw, right, to see like how many people have voted yes, how many people have voted no, etc, etc. Coming down, we have something called yes attestation and no attestation. Remember the attestation part that we're talking about in finalize. This is what we'll be looking at. Okay, so this one, yes attestation and no attestation. This is important, right? We need to not only get yes and no votes which are encrypted, we also have to prove that they are actually genuine, not spoofed. So where is that? So we're gonna look into this function as well. Reveal handle, we're going to accept the app context. Okay, so the context of the app, and then the yes votes that we got, a big integer. Okay, number of votes we got, and then we're going to do handle to x, and then we're going to use the context and call attested reveal. So basically this is a function that will allow us to fetch the attestation of this particular execution and also decrypt it. So we're also passing some of the parameters over here to enable that, and then we are going to get the plain text of the result, basically plain text of the decrypted attestation, and then we're going to encode it so that we can pass it as a bytes to the smart contract, and then we're going to return those signatures and other details over here. Okay, very simple straightforward stuff. Okay, Inco handles everything for you, all that fetching attestation part and all you have to do is just call the right functions to fetch them, and then we do write contract because we are calling the finalized contract. So we send the proposal ID, and then we send the handle, yes handle, and then the value of the yes attestation, and then the signature of the attestation because we have it over here, right? So we have the decryption attestation, that's what we are attaching here. So we are attaching the attestation and then the signature of the attestation for yes and no both. So this will finalize the entire stuff. So when you finalize it, it means that you have verified it end to end and it is finalized. So either the proposal gets accepted if the yes is majority of the vote, if it is no, then it will reject it, and then we're just waiting for the transaction, and then we're saying, hey, it is finalized. Everything that we've seen here is completely trustless as we talked about, and it's very simple, and Inco guys are doing really great job here with this because they're handing this complex infrastructure to you and then giving you out all these methods and operators so that it makes it very easier for you to get started also. And as we saw that we're building this on top of a simple Solidity contract. The amazing part is that they just went live few days ago on base mainnet as well, so you guys can check it out that as well. And with that said, thank you so much guys. We'll see you in next one.